with that, reminder to our first session on intrinsic dynamics, intrinsic mechanics, and finger coordination with two speakers, Madhu Venkasedan and Alberto Rodriguez. And while Madhu changes screen, I want to say just a few words about Madhu. I have known Madhu since he was a graduate student, a very impressive graduate student, at the time already working on finger coordination with Francisco Valera Cuevas. But then he moved on to go to Harvard for a postdoc, and he did some amazing work on feet, moving from fingers to feet, but again, focusing on the multi-link structure of the feet, including barefoot running. Since then and now at Yale, he has addressed a number of highly fascinating, to the extent of exotic topics, all focusing on the interplay of biomechanics, dynamics, and control. And the last exotic topic that I've seen Madhu present was on jumping frogs. I don't think he's going to talk about that now, but I can only say I love all the topics that Madhu has covered. So with that, please, Madhu, begin.
Thank you, Dagmar. Thank you all for inviting me and the very kind introduction. I'm going to talk today about some work that we've been doing on fingers. And I'm completely amazed by the kinds of things people can do, and not being a roboticist, I'm also quite amazed by the things that robots can do. But I agree with Ard that there is still some gap to be bridged between how robotic hands can work versus human hands can work. For maybe one of you is in Tokyo, and I believe Tokyo is not in shutdown. And if you have the chance, around Ginza, occasionally there is this artist whose video is choppily playing. In reality, he's less choppy. He's incredibly graceful in using his hands to handle this very heavy glass sphere, making it mimic all kinds of other dynamics. I'm using this video to really point out some incredible interactions we are capable of having with objects using our fingers, and also to point out things that I'm not going to even begin to reach in my talk. So although human hands are capable of incredible dynamical behaviors, I'm going to be talking about a much simpler problem of how do you stay static and push on something with your fingertip. I will first acknowledge Neelima Sharma, who's a senior graduate student. Hint, hint, she's looking for postdocs. She's done amazing work on fingers and a broader set of problems. Let me use my mouse pointer as a laser pointer. So she's also now working on more general approaches to controlling contact in any linkage system and mechanics of mechanical linkages itself. And I also wish to acknowledge the physical and engineering biology program at Yale, which funded Neelima through this work. Okay, well, so let me get started. The fact that humans are capable of such incredible feats often hides a lot of intrinsic challenges that our combination of our nervous system and the mechanics of our hands overcomes. So when you look at what it's capable of, we often maybe fail to not see what are the problems that it had to solve in order to be there. And there I really value the insights being generated in the world of robotics, where we are effectively playing God and constructing something from scratch and are faced with some unique problems. The next video I'm going to show probably will not play very well on this. You will see a person go to a robot that's trying to do some form of control of the interaction force. And this person first holds the robot very softly and then holds it very stiff. And the minute he holds it stiff, there is this very high frequency instability that sets in. The robot starts vibrating vertically, which is, well, maybe to make a point, it's so fast that at the frame rate that Zoom can transmit, you don't even see that very clearly. So that is a broad class of problems under the banner of contact instabilities. And the contact instability there refers to maintaining and regulating the force of interaction between a manipulator and an environment, and well-known problems when the environment becomes very stiff. That was sort of where I started thinking about some problems associated with finger contact. And as you watch that very brave person trying to touch this very strong robot, you also notice that one of the first things we have to do to grasp anything is use our hands and fingers to push. He's using what you would call a power grip. The whole palm wraps around the object, but occasionally he also uses the tip of his fingers to press on a fairly stiff surface. So the first class of problems we looked at was, how do you initiate contact? Initiating contact is really about moving towards a point, and upon reaching there, being able to exert the forces that we want to. This was work I did quite some time ago with Francisco Valera Cuevas, who's at USC. At that time, he was at Cornell. That motivated me to ask an even simpler level of question, which is really not being looked at all. And I would bin under the category of contact instabilities. And this instability is what happens when you want to push with your finger and say, just keep it static. Your objective is push, maybe push as hard as you want in the one example I'm going to show, and not let anything happen. So be as boring as possible. On occasion, the following happens. Your fingers will snap and buckle into these very hyperextended postures. If you are trying to do something very precise or dealing with slippery objects, that would be the end of your attempt. And if you notice the clock, that behavior is incredibly fast. So in that one example, that person's finger went through what looks like buckling, and I later make a brief point that it is in fact identical to standard structural buckling. That is a really fast event. It happens in the order of 20 milliseconds. To give you an idea, in 20 milliseconds, the information from various sensors within your finger that your joint angle is changing would have propagated not even up to your elbow. Forget about reaching your spine. So it's a really, really fast event. So in today's talk, what I'm going to talk about is this type of instability, and really ask a question: why don't we see it all the time? How do people prevent these from happening? There's a very simple solution. Just make your finger as stiff as you can. In fact, just pot it in concrete and it's never going to buckle. That's at the opposite extreme, perhaps, of what we want to do from the point of view of dexterous manipulation and things like force instabilities, where we want a very compliant finger. So really the question has in the back of its mind an objective that you want to be as soft as you can and yet not buckle. Okay, this brief talk is going to have 4 pieces. And the broad question that I'm going to try to assess is what governs postural stability of human fingers during contact. Notice I say generally fingers. I'm going to use a model system. The mouse of my lab in these studies is the index finger. I will tell you a little bit about what we learn by thinking about how we initiate contact, and then talk to you about how we prevent these instabilities and what can be learned from it. Okay, first, a little bit of anatomy to give you a sense of the complexity, but at the same time, the appeal of the finger. That's a skeleton showing the index finger where my mouse pointer is moving right now. That is the metacarpal. By metacarpal, I'm meaning it's the thing that forms your knuckle. And the 3 segments of your finger are out here. And the finger, like a lot of our body, is like a marionette toy, right? So your nerves, your muscles and tendons are the strings that is pulling on the system and trying to control it. You can give labels to these as extensors that cause your finger to extend or flex. But mathematically, one simple way to think about it is when I have a neural activation signal, at its simplest extreme, you can treat a muscle as something that converts it to tensions in the cables that are driving the system. And the geometry and how the cables are arranged around the joints create a lever arm that can lead to joint torques. And ultimately, these torques are driving your system. When we say feedback control in this context, we want to know how are these torques responding to things that happen. When we say elasticity of the finger, we mean, well, how are these torques arising because my muscles being stretched and so on. So in that study, we did a slightly more detailed physiological or electrophysiological attempt than I've since attempted. We recorded from all 7 muscles that control the index finger using fine wires that were inserted into the muscle. In reality, it's less painful than it looks. These needles get removed, the wires get left behind. And then we get incredibly clean recordings of the muscle. And we were, for example, able to tell apart the fact that when people move, pardon me, that was unintentional. When people move, they switch their coordination pattern from one initial coordination patterns, which you can think of as a 7D vector in this activation space, to another 7D vector in activation space, just in the nick of time before they make contact. So this is time. The dashed line is when the finger makes contact. The red region is when the finger is still moving. And I'm showing the angle between the current instantaneous recording of the coordination pattern with respect to some reference recorded in static conditions. And what you see is the activation pattern swings around to match the steady state activation pattern just in the nick of time that people make contact, which we can show translates to a switching of joint torques appropriate for moving the finger or applying forces. And that was the end of making contact. And that was, in my mind at that point, it was the end of thinking about contact problems and the static problems in fingers. I was mistaken because I just had not really thought about this issue of postural instabilities. So here is one example that the same video I showed you, this is a digitization of a different video where 0 is when we first visibly detected some degree of growth of that joint angle. Right? So if you want to really think about your finger and mechanically in the plane, it's a 4-bar linkage. There are 3 bars. The tip, when it's not slipping, let's approximate it with a hinge. That's the knuckle, and when my whole hand is not moving or I'm in the frame of my hand, that's another hinge joint, and that forms a 4-bar linkage with 1 degree of freedom. And the fundamental problem is that this degree of freedom, when under compression, becomes unstable, and it becomes unstable in this very incredible way, where that joint angle, the distal joint, is growing exponentially with a time constant of between 9 to 23 milliseconds. This is from 9 recordings of fairly rare instabilities. You really have to sit next to the person and make them push as hard as they can to occasionally see these instabilities. Where do these instabilities arise from? That's a topic in itself. We can talk about fingers, but we can talk more generally about kinematic chains, but they arise really from the underlying governing equations. So think about the 3 terms. The 3 terms, that is acceleration related terms. This is a lumping together of centripetal terms, Coriolis terms, gravity terms, spring terms, viscosity terms. I've lumped everything in there. Forget about this for now. I'll tell you what this is in a moment. And those are the torques driving the joint. The term here is the key. Lambdas are the reaction forces because the tip is not moving, it's in contact. And those reaction forces get transformed into joint torques depending upon the geometry of the finger. If I use external torques that correspond to exact static equilibrium, that is still an unstable system. Where if I start that finger from a posture that is slightly different from the posture of exact equilibrium, it undergoes these very rapid snap buckling events. You can do a slightly more detailed analysis and show that this is almost exactly the same as a static Euler buckling of a slender column.
12
Okay, but
minutes, Madhu.
yeah, thank you. So the lesson really is that feedback control cannot stabilize the finger's posture. So what can? Well, what can, a little bit of a hint comes from looking at a study such as this, which Neville Hogan conducted, trying to mimic a drill press. So a person takes a handle, pushes on a wall. The handle can be flat, the handle can be pointed, but the part where the hand is holding it is fairly rigid or can swivel freely. And what they found is as the system becomes increasingly unstable, you see the peak force that a person can apply decreases. And this is not surprising in many ways, but the real question is, how do you stabilize? One way of stabilizing is to stiffen the entire structure. Can similar thinking help us deal with the finger? Short answer is it's a little complicated because muscles themselves have variable stiffness. So from analysis of that governing equations, you can derive a minimum stiffness that is needed to stabilize the finger. But muscles, when activated, don't only produce tensions, but also stiffen. And the kinematics of the finger translates that stiffness to an effective stiffness at the joint. So this is an example of how the stiffness of muscle depends on the load approximately linearly. For stability of the finger, the minimum stiffness I need scales linearly with the contact force. So maybe muscles intrinsically can deal with this instability. Can they? Short answer, no. And what we did was solve an optimization problem to find the activation patterns that maximize the force. That's that. Take that activation pattern using models of muscle that capture this activation dependent stiffness, calculate the stiffness induced by muscle, use the mechanics to ask what is the minimum stiffness required for stability, and we find that at maximum forces, the finger is unstable in almost a posture independent way. So how do people stabilize? And this is really the punchline. What we did was ask people to push as hard as they can. We record the maximum force they can produce. We also recorded surface EMG from the big flexor muscles, and then added a splint to stabilize their finger, essentially stiffen their finger. And we find that the maximum force they can produce increased by about 50%, and the aggregate EMG from both of these muscles also increased by 50%. So it's really that stabilizing the finger or stiffening the finger makes people stronger because their muscles can produce greater forces without destabilizing the finger. The same is true if I use a partial splint and leave that joint free. I mean, it's a 1 degree of freedom system, so I can stiffen some subset and stiffen the whole structure. And there is reasonable or some amount of correlation between increase in EMG and how much increase there is in the forces. Okay, so I'm going to finish with the following statement. If I claim that at maximum forces, for example, in this posture, the minimum required stiffness is higher than the stiffness due to muscles, and previous work by Francisco and many others have shown that humans essentially scale the activation pattern they use to reach maximum forces, I can show that you will be unstable at all forces. So how can we ever be stable? The answer is very straightforward. It's at maximum forces, I have really unique activation patterns that get me to the maximum force. But what we've shown is people really do not go to the maximum forces. They voluntarily stop at less than maximal forces. At that point, there is enough redundancy within quotes to allow you to co-contract your muscles and stiffen your joints. But what co-contraction does is it lends stability, but it's going to cost in two different ways. It decreases the maximal force you can produce, but it's also going to make you stiffer in your tip, which is perhaps not the ideal thing for very precise manipulation tasks. Okay, I will end by just plugging for forthcoming things from Nilima, where some of this thinking and analysis, we've been able to show that finding activation patterns that will always maintain stability is a linear convex problem, which just opens up very simple ways to solve a large class of problems. Thank you for listening, and I stop here.